One to the Black Hole and ICTP summer workshop on mathematics for physics. Today is our first day, and this is going to be a 4-week, very intensive workshop in which you will learn a lot about mathematics and how it impacts various areas of physics. Of course, many of these developments were triggered by particle physics, but now these methods have gone into all branches of physics. In fact, even places where you would least expect them, such as control systems, artificial intelligence, other places too. This workshop has been made possible by help from the Abdus Salam International Center for Theoretical Physics and by support from Dr. Amir Iqbal, who you will hear in just a few moments, but let me introduce you to him. He is absolutely the most talented mathematician that Pakistan has produced. He received his PhD from MIT, then he went on as a visiting professor at Harvard. He has worked with the great people in the area of string theory, such as Kamran Wafa, and he has been quoted by Edward Witten and other very important people in this most advanced and esoteric branch of mathematics and physics. This workshop is made possible only because we have some wonderful instructors here. So Dr. Hassan Azad, Dr. Jamil, Dr. Ahsan Zaid, and we are missing Waqas Masood, who will not come today. But these four instructors, I'll be the fifth, will cover branches of mathematics according to a schedule that I will put before you now. This is going to be quite intensive. There will be 90-minute lectures, and starting at 9:30 in the morning every day. So I will be teaching differential geometry. Dr. Waqas Masood will teach differential equations. Dr. Ahsan Zaid, he will tell you a lot about linear algebra for quantum mechanics, but I think he's going to go be much beyond that. Dr. Hassan Azad, he is the only true mathematician amongst us all. And we are always in awe of him because he's a man for proofs rather than application. And there is Dr. Jamil Aslam, who will tell us about the most important things that we need for particle physics, causality, Kramer's chronic relations, and so forth. So all that comes under complex variables. Okay, so that is a very brief introduction. You can see the schedule. This Friday, we will not have a class because it's the 14th of August, Independence Day. And so the Friday class will be shifted to the next day, that is Saturday. After these two classes, with a little break in between them, we will have lunch, and so you're invited there. All registered participants are invited there. And then that'll also give us time for discussion. You are welcome to ask questions during the lecture, because this is meant to be a school. This is meant to be back and forth. It's not one way. But then you may need more time, and so for discussion on the board, we will have some time reserved for that. Sanan Qureshi, who you've been in contact with, he will take attendance, and attendance is only for those who want to get certificates. Otherwise, anyone can come and sit in the lectures because the black hole is an open public space. But if you want to get a certificate, then you will have to be regular. The certificate will be, of course, from both TBH and ICTP.
Those who are not registered, if they start asking questions, then it will take too much time. So initially, I think we should allow only the.
Well, let's talk about that. I don't think if let's see how it goes. So, Dr. Hassan Azad made the intervention which you could not hear, and he said questions should be limited to those who are registered. And I said, if that comes about, if there are too many questions, then we will adjust our policy appropriately. But maybe there won't be too many questions.
No, there are established people sitting there.
Well, let's see how it goes. Let's see how it goes. But the whole purpose is learning. I just want to say one thing, that the topics covered over here are going to be quite advanced. And as Dr. Hassan Azad said earlier, the idea is not to give you all the details, which you can only get by working through the problems, but rather to give you a flavor of what mathematics for theoretical physics is all about. So with that, I will ask Amir Iqbal to tell us something about how he sees mathematics in physics. I should tell you that oh, good to see you, Amir. I see you now. Okay. Amir, if I am correct, you are the head of the theoretical physics division at the Turing Institute now?
No, actually, this is not an institute. It's just basically an AI company which does basically test AI models, basically.
So he is teaching AI to do things like supersymmetry and very difficult mathematical problems also. And he told me he's having a lot of fun doing this. So, you know, when you go to AI and ask it to do very complicated mathematics, whether that's group theory or it's differential equations or topology or whatever, you can now these days ask it anything. Well, AI has to learn from humans, and that's what Amir is teaching AI to do. So Amir, over to you, and we look forward to hearing you.
Thank you, Pervez, and thank you for the opportunity. It's actually wonderful to see that the Black Hole is conducting workshops, and especially a workshop on the two pillars of theoretical physics, quantum mechanics and GR, and the mathematics which is necessary to understand these things. So I was thinking about, after your email, I was thinking about some connection between mathematics and physics and how to actually talk about that in a few minutes. Basically, it's a vast topic. And we have heard a lot about mathematical physics, but there's a whole field for many, many years now called physical mathematics, where physics is physical insight into systems actually helps mathematicians understand some mathematical concepts. And that has been a very successful program. So what I did is I was thinking of what to talk about because it's a vast area. So what I thought was that I'll pick a mathematical object, and then we can just follow it, how it appears in physics in different contexts. And I started looking at for what object to see. And I thought maybe everyone is familiar with matrices, basically. So that's an object which is built out of matrices, and which appears in physics all over the place. So what I did is I have prepared like three dense slides. The purpose of the slides is not, I will not explain everything in the slide because that will take too much of a time. So, but it's like a thing which students can not understand something and aspire to understand that connection. So let me share my screen. Can I share my screen?
Zohaib, screen share. Still can't see it, but we are seeing you.
I know. Okay, I think screen share is turned off, so I will not be able to share the screen. But what I can try to do is, oh, I can share it now. So let me share that. All right.
Yes, we can see it now.
Yeah. So I was thinking of, SU2. What would be more interesting and simpler than SU2? So essentially 2 by 2 matrices of this type with A and B are complex numbers, where A mod square plus B mod square is 1. So geometrically, this is just S3, basically. And it has an interesting connection with the rotation group that we study usually, SO3, that it's the double, what is called the double cover of that. And this fact has amazing consequences. One of the amazing consequences is that of an electron, when rotated by 2 pi, everything we usually understand that everything we rotate by 2 pi comes back to itself. But no, electron rotated by 2 pi does not come back to itself. Only by a rotation by 4 pi does it come back to itself. So that's an amazing consequence essentially of studying this structure, which is called special unitary group of 2 by 2 matrices. The other interesting thing about this group or this set of matrices basically is that this is the backbone of the Salam-Weinberg electroweak theory. That the Salam-Weinberg started with this group SU2 and another one of not similar but something similar to that, and then came up with this interesting idea basically that if we start with this symmetry, we can break it down and obtain the world, a part of the world that we see around us. The photon, the massless photon, and its cousins, basically, the W particles and the Z particles. So essentially studying the geometry, topology, you can say, of this group leads to this kind of development. The other interesting thing, more I would say modern in some sense and more closer to my heart basically, is that if we study this gauge theory, we can engineer these gauge theories from geometry. So these are surfaces which were studied by Hirzebruch a long time ago, and these are called Hirzebruch surfaces, which are labeled by this integer n. And you can think of them essentially as spheres fibered over spheres, a P1 bundle over P1. And there are these various geometries can be used in string theory, M theory, to engineer various kinds of gauge theories. And in those gauge theories, then particles appears in various SU2 times SU2 multiplets, basically. For example, this is spin half, spin 4, spin 0, spin 7 by 2, and so forth. So that's a very interesting connection between SU2 gauge theories, geometry, and the physics. Since I have just like a few minutes, I don't want to take up time away from that, but I will actually show you something interesting, which is so this is a very interesting animation, and I've done. When I used to teach quantum mechanics and talk about SU2. This is similar to this example I used to do in the class. It's called the belt trick.
We cannot see the animation. We just see Wikipedia over there. That's.
Oh, just a second. I should share the desktop. Okay.
Okay. Yes.
All right. So that's a very interesting one. So this essentially shows again the same idea, basically, that rotation by 2 pi does not bring certain systems back to their initial configuration. Only a rotation by 4 pi will bring it. So if you focus, for example, on this particular strip, this strip is connected to one side of this cube. And this strip, if you look at it slightly longer enough, so let me show you where it does it. So now, if you look at it, it's untwisted. But after 360 rotation, it is now twisted. And then again, it is untwisted after a 4 pi rotation. So this is, again, a very version of it. There are various versions of this thing. For example, Penrose's book has a very interesting one, very similar to this one as well. So this is all essentially, let me see how not to share. All right. So this essentially all has to do with essentially the geometry and topology of the set of 2 by 2 matrices with certain properties. And this leads to amazing results related to mathematics and physics. So I hope that what people learn, what students learn in this workshop, they will take away and then build on it to understand better ideas and come up with new developments in theoretical physics. Thank you, Pervez.
Okay. Well, actually, that was a wonderful introduction to the whole idea of. Hassan wants to say something, so then you'll need a microphone. Otherwise, he won't be able to hear you. Yes. Okay.
Assalamualaikum, Amir. Ji.
Hassan.
I wanted to ask you, have now a lot of experience. What would you advise students how to use AI for homework and for learning?
Actually, this is something which Pervez and I talked about a while back. Look, my point of view might not be the point of view of a lot of people, but my point of view is that it's a tool. In the 80s and 90s, like in maybe early on 70s, 80s, lots of books. People had books, and they could go through those books and understand it. In the 90s, then the internet came. All those books which were hard to get became very easily accessible. But still, someone has to go through it. Someone else knows it. Someone else wrote the book. Just by having the book doesn't mean I know what's in the book. So similarly for the AI, it can tell you the answer, but the question is, do I understand the topic well enough to understand its answer? And it can explain the answer to me in a very detailed way, but still I will have to make an effort in order to understand the answer. And this has been the case. If you have noticed recently, there have been a lot of optimism and a lot of news around that AI, especially GPT, has proven, GPT 5.6 has proven conjectures related to mathematics. And only later on, people try to understand that although they prove the conjecture, a lot of stuff that went into the proof, the theorems, were actually not proven or not correct. So we have to be very careful with this thing. The performance has a lot of volatility. It can tell you very complex things correctly, but then fail on very simple things. So it's, again, for students using the AI, I would say buyer beware. It's your own responsibility, basically, to understand whether what it has given is correct or not. So my point of view, again, is nothing beats pencil and paper and working out things in detail by yourself. One can take help from the AI, but still it has to be done by yourself.
Okay, good. So that was actually a wonderful introduction to what I am going to talk about, which is differential geometry. Amir showed those very complicated manifolds, those surfaces generated, of course, by AI, of those things which are rotating around and twisting around. but I will take a very lowbrow approach to this. First, I will show you pictures, and then we will get into the mathematics of it. But first of all, I want to show you what this course on differential geometry will be about. Today's lecture will be general. It'll be about what differential geometry is all about, and in particular manifolds. And then we'll get into the issue of what are tensors, and in particular the tensor which tells you how much the distance is between 2 points. That's the metric tensor. We'll deal with surfaces that are complicated, where the shortest distance between 2 points is not a straight line. It is what is called a geodesic. And on this complicated surface, we will then talk about covariant derivatives, curvatures, and then maybe I will skip chapter 4 and go to chapter 5, but hopefully Dr. Hassan Azad will tell you about Lie derivatives. I might also. Let's see how it goes. And then we leave the traditional approach aside and look at differential forms. That's a more compact way of looking at various aspects of differential geometry, and it's an attempt. The goal in this is to get rid of indices. So once you have something without indices, indices are particular to a particular frame of reference, and the whole goal of geometry is to get rid of details and get the overall picture. This leads us to the integration of what we will see, what we will define as forms, and then the Stokes theorem. The last 2 lectures will be on general relativity. And we'll end with the derivation of Einstein's equations. Of course, we could do this differently, and we could go to other areas of theoretical physics like symplectic forms. We could do the Aharonov-Bohm effect or other things where these ideas have application. But let's see how it goes. All this will be adjusted depending on the level of questions and so forth. It all starts with Riemann. Bernhard Riemann, born 1826, died 1866, so 40 years. In 40 years, he produced the most amazing mathematics. He not only invented differential geometry, but the Riemann zeta function, so much about integration. You've all heard of the Riemann integral. Well, but the story of differential geometry is an interesting one, because he was a person from a village. गाँव का लड़का था. He went to Gauss, who was the greatest mathematician in Germany at that time, and said, Professor Gauss, give me a research problem. So Gauss said, okay, Euclid has been around for hundreds of years, and his assumptions in geometry haven't been challenged. He says that 2 parallel lines will never meet, but I want you to create a geometry where parallel lines will meet or they will diverge. And so Riemann said, that's very hard. He went back to his village. He had a nervous breakdown, but 2 years later he came back and he had it all written up, and then he became famous. So now let's talk about manifolds. So what is a manifold? A manifold is anything. It can be this piece of paper. So there's a surface over here. Even simpler as a manifold is a straight line. I draw a straight line, and that's a manifold. Now, what is a manifold? If I am sitting at a point, so manifold is a collection of points, but not any collection of points. It's got to be an infinite number of points, and there's got to be some sense of distance between the points. what they call metric spaces, so that you know which point is close and which point is far, so forth. So a manifold, whether it is in one dimension, which is a line, or two dimensions, which is a sheet of paper, and this sheet of paper can be flat like this, in which case it has no curvature, but it can be also of this shape or of this shape, or it can, or if I have a sphere, that's also a manifold. These are all different types of manifolds. But the point is that when you are on a manifold, if you're at one point over there, then you see the world as being flat. So think of yourself as an ant, chunti, and as you look around, you see, the world is flat. You make a triangle, you add up the angles of the triangle, you get 180 degrees. And that is in two dimensions. Of course, you have to have 2 dimensions to make a triangle. So let's first ask the question of whether, of different shapes, is this a manifold? And the answer is yes. Because if I am, think of yourself as being an ant at any point on the manifold, and it appears flat to you. Of course, there's, if you're an ant on the other side, then that will also appear as a manifold to you. So that's good. Well, is this a manifold? And here, what I've drawn is a parabola. The parabola goes from one end to the other, and it's infinitely long. So, like a line which is infinitely long, this too is a manifold, because if you're standing at any one point on this parabola, you will see it as being flat. Just like if you're on the surface of the earth and you look around, you see, you don't see the curvature of the earth. Similarly, if I ask if this is a manifold, yes, of course it is. So is this a manifold. But, this is a circle, and you see that if you zero on to, let me see how to, so here, if I take this little piece over here and I blow it up, I'll see it as being flat. So yes, this is of course a manifold. But now this over here is not a manifold, because it's not a manifold at the point where where these lines cross. Because if you're standing at that particular point, well, then you see that it's more complicated. You don't see it as locally flat. Let's go to 2 dimensions. In 2 dimensions, yeah, this is a manifold. Any question on that? No, this is, the people believed that the world was flat for a long time. That's because they were not able to look far enough. Here is an example of 2 spheres, 2 cones, whatever, joined together at one point. And just like with the figure 8, this also is not a manifold. whenever you think of manifolds, think of yourself as an ant. And this I got from Quantum magazine. It's a very nice picture. And you can see that every ant is thinking of itself as being an observer, and to that observer, it all looks flat. However, looking from outside, we can see that these ants are crawling. Of course, we are outside observers, and we live in 3 dimensions. But the ant imagine that the ant is not able to look up or down. The ant is living in 2 dimensions. We are living in 3 dimensions. Now let's come to more complicated surfaces, manifolds. This is a torus. A torus is like हमारे यहाँ बेगल नहीं होता है. What donuts होते हैं. This is a donut. So a donut is not like a sphere. It's there's something different about a donut as compared to a sphere, right? Why? Because for a donut, you can go around. Okay, first of all, if you look at what is called over here the trivial loop, well, that's just like as if you were on a flat surface, or that's on a very simple surface, that of a sphere. Maybe there's you can make that loop smaller and smaller, but an observer on that loop will see locally flat spaces. But there's something different about this and a sphere, because there are 2 loops now on which an observer, on which an ant can go around. And there's number 1, you see, loop 1, it can go all around, or it can go the other way on the donut. Things can be more complicated. This is a manifold which is said to have genus 2, GENUS, whereas genus 2, genus 1, yeah, genus 1. This has genus 2. We'll discuss later what genus exactly is. Not very much, but a little bit about that. And now, before we get into some mathematics, I'll show you a final manifold. This is called a Mobius strip. But let me show you this one first. So this is computer generated, and it's much less complicated than the ones that Dr. Amir just showed you. But here, if you take a strip of paper, a rectangular strip of paper, and you twist one end, and then you join the 2 together, glue them together, then this is the sort of manifold that you get. Is this first of all, is this a manifold, and why? It is a manifold because it is locally flat. Every point on that is locally flat. I mean, an observer will see his world as being locally flat. So it is that. But it's now very different from a flat sheet of paper, because if you travel around it, then if you start from one side of the paper, you will end up on the other side, like over here. So again, it's wonderful how AI can generate these things, and artists would have a hard time doing this. No, artists can do this. There was that famous artist, what was his name? Escher. Escher. Escher could do wonderful things, but it requires a lot of imagination. Actually, we have an Escher in the black hole also. Yes. He's not here right now, but but yeah. So now let me. So Mobius, who was I think 19th century, he's a mathematician. He said, "Let me make a resistor, which is a Mobius strip." So you see, the plus and the minus are battery leads. Those are you connect them to a battery. Now, current flows from positive to negative. And so you see that current is flowing on one side in one direction, and on the other side in the other direction. It goes from the positive, it has to go from the positive to the negative. But then somewhere along, it flips. And when it enters the negative terminal, then again it is in the same direction. And so finally, we have all sorts of complicated shapes which are possible, and one of these is the Klein bottle. You see that this is, of course, a manifold, but and it has to intersect itself. So it comes back and has to re-enter. I don't know how it is exactly described in topology. It is not the solution of any simple equation, is it? Okay, but Klein invented this. He's got a handle. You can see one handle over here. And what is the genus of a Klein bottle? Do you know?
Seems to be one, but I don't know.
Okay. So, yes?
How do you know that a Klein bottle is a manifold?
Because it is locally flat. You see, it's everywhere it is locally flat.
But at that point where the net is joining the main bottle.
That is where the problem is. Where it comes and joins. So like the figure 8 is a manifold except at one point, and here it is at where it re-enters the volume. So I think, I don't know very much about this, after all, I only know a little bit of differential topology. Yeah. That is a beautiful point. And so, what's your name? Mujib. So Mujib from the audience said that if you have a Klein bottle in 4 dimensions, then you can avoid the intersection. And so in 4 dimensions, this will be a manifold without any disturbances to it and will not have a handle. Yeah.
So this is a projection.
No, this is in 3 dimensions. We can't draw a 4-dimensional Klein bottle. Yeah.
So then the question comes, if something is intersecting itself, then if we go into a higher dimension, we can make a manifold out of it.
So, question from the audience, a statement. What's your name? Ahmed from the audience says that if I have a figure 8, then if I go to one higher dimension, then I can avoid the crossover. And that's absolutely correct, because then I can go below that. And so like the Mobius strip, it will be all continuous. So it will be, the point is that you will have a differentiable manifold even for a figure 8, but in 2 dimensions.
But if we go into a high enough dimension, we can make anything into a manifold.
No, I think what you're talking about is desingularization. I think.
Okay, so I am only making one little claim, that is, anything that looks flat is then a manifold. What we are interested in this course is differentiable manifolds. And so I think now we need to get into some mathematics. यार ये मिटा दो. Yeah, so pictures are nice, but where the real effort comes in is when you put them down on paper. How many people over here are familiar with basic topology? Open sets, closed sets. So 1, 2, 3. Yeah, so what I'll do is, I don't know very much about it also, but I'll tell you what I do know. So let's start with open sets. In fact, we're only interested in infinite sets over here, not interested in finite numbers of points. Infinite number of points, and infinite, very badly infinite, so that if I take any 2 points, then no matter how close they are, there'll be an infinite number of points in between them. And that happens for real numbers. Okay, then also you can arrange the numbers so that the smaller numbers are on one side, the bigger numbers are on the other side. This is good enough as far as set theory is concerned for me. So what is an open set like this? This over here denotes that open on this side, open on this side. So there are an infinite number of numbers between 0 and 1, but does not contain either the number 0 or 1. And you say, what does it matter? I'm just excluding one number, so it can't make a difference, but actually it makes a huge difference. Because your differentiability is lost. What happens in differentiation? You take a point to the right, a point to the left, and very, very close by, and then you make the distance go to 0. But if you can't take a point to the right or a point to the left, that means differentiability fails. So this is an open set. This denotes a closed set. So this does contain both 0 and 1. And if I have this, then of course that means that 0 is contained, but 1 is not contained in that. Okay, so that, what about R? I don't know how to write this R very well, but R, I'll write it this. R1 is the line from minus infinity to plus infinity. And since infinity is not a point, this is an open set. Hasan, please feel free to contradict me at any point. मैथमेटिशियन से हमेशा डर लगता ना. अच्छा. So this R1 is an open set. Well, R1 is what? It's just the straight line, but we can easily go to 2 dimensions, in which case you have all the way here, all the way here, and that's what is called R2. And then after that, R3, and then the imagination takes over, and then you have Rn. So Rn is the space with n dimensions, which means that every point in Rn is labeled by n coordinates, 1 up till n coordinates. And you know, there is no harm in letting n be as big as possible. So all the time we deal with infinite dimensional spaces where n goes to infinity. Of course, you can't imagine these things, but this is where mathematics takes over. Okay, so now the next concept I will need is the concept of function. I know these are very elementary things, but not everybody is fully familiar. So a function which I will denote by phi is a machine which takes a point P on the manifold as its input and gives a number x. And so you could say that x is equal to phi of P. In one dimension, P would be a point with a point on the line. In n dimensions, this P would be a point on an n-dimensional manifold, and the function will act on P, so phi, so the machine will act on this input and give you n numbers. So this x in n dimensions will be n different numbers. Okay, so let's think of 2 dimensions now. If I have see, I can't draw very well, but you can imagine that this is a sphere. Here is a point on the sphere, so P is a point on the sphere. And so how are you going to describe this? Okay, so the point is the real actual thing which is there. It could be an ink spot that you have put on the sphere. But then you need coordinates. And let's call x the coordinates. So what would the coordinates be? You could give theta and phi. But then that's not necessary. You could use some other way of giving coordinates. The point is that here is P, which is a dot on a 2-dimensional surface, and so x will be actually 2 numbers. And you can imagine now an n-dimensional manifold. There's a point on that manifold, and then the coordinates will be n in number. Okay, then what we need is uniqueness of these coordinates. So if I have a coordinate P, if I have a point P, I should get just one number as the coordinate, or one set of numbers as the coordinate, which means I should be able to invert it. So if I'm given X, I should be able to get back to the point P. What I need then is the inverse function. Which means what? That I give it the coordinate X, and out comes P. And now let me take these two machines and join them up. So P phi, out comes X, but then I'm going to take this machine and put it over here. The inverse, and out will come P itself. Or let's complete this over here. P is equal to phi inverse X. All right, so look at it this way. What is this? Let's write this mathematically. So P is equal to, P is equal to phi inverse. What is going in? X. But this is phi inverse of phi of P. Or we write this as phi inverse composed with phi acting on P. So this here is the unit function. Phi inverse phi is just 1. And the other way is also true, that phi inverse is 1. Well, you see, this is not altogether trivial, because this is in n-dimensional space, and this is, all these x's and p's are in n-dimensional space. That's just to tell you what phi and phi inverse are. Now we will come to the concept of transition function. So first let me define something which is called a coordinate chart. This coordinate chart is an open set together with a function phi. This u is we talked about the open interval. The open set u is of course just an extension of that. So you don't have boundaries included in that. Let's take a manifold. And let me take let me call this U1. So U1 is an open set on a manifold. Manifold can be in any number of dimensions. And let's take a point over here, P. then the function phi will map this into Rn. Nothing new over here so far. Let me take another open set which has an overlap with U1. So there is this set over here, set of points here. What do we call this in the language of set theory? Yeah, the union of U1 and U2. Intersection. So this over here is U1, U2. Okay, so now here's the point P, which takes where the function phi1 takes it to a point over here. Let's call that x1. And there's a function phi2 which takes the same point P into x2. So, and this is of course also in Rn. Okay, so if I know x1, do I know x2? Assuming that I know the function phi1 and phi2, yes, but we need to know how to get there. So let's see how that works out. In other words, if I give you the coordinates x, y, z on a sphere with x squared plus y squared plus z squared equals 1, let's say, can you tell me what the polar coordinates theta phi will be? Yes. And the other way around, if I give you theta phi, can you tell me what x1, x2, x3 will be? Yes. So that will be the whole idea over here. Okay, so here x1 is equal to phi1 of p. x2 is equal to phi2 of p. Same point P, and from here P is equal to phi1 inverse of x1, and from here P is equal to phi2 inverse of x2. And so obviously if I put this into this, then P will be equal to phi1 of so P is equal to, yeah, which is phi1 composed with phi2 inverse. And this is what is called the transition function. Now, as we discussed earlier, we are interested in smooth manifolds without any holes or disturbances in it. And this means that the transition function has to be infinitely differentiable. Mathematicians like to use this symbol, C infinity. This means infinitely differentiable. You can take any number of derivatives anywhere where this where differentiability has to hold everywhere, and it has to be infinitely differentiable. Yeah. Why do we want differentiability?
Infinitely.
Because you want things to be very, very smooth. You see, suppose you take a function like this. Y is equal to magnitude of x. This is equal to x if x is positive, it's equal to minus x if x is negative, and it's smooth. Smooth everywhere except here. And so it's not smooth enough for many things.
What does that mean exactly?
What that means is, for example, okay, in terms of physics, what does that mean? If, let's say, this means that your velocity is constant and negative, and then becomes constant and positive, then that means your velocity has changed by a finite amount in zero time, which means the acceleration is infinite, which means by Newton's law, the force is infinite, and so that's an unphysical situation. When we are solving differential equations, for example, we insist that there be infinite differentiability, except at some point where it should not be. So, for example, if you go to the boundary, then the value changes suddenly. But elsewhere, it has to be infinitely differentiable. Any other questions? Yeah. Can you speak? यार mic इनको दे दो. हाँ.
Can you hear me now?
Yeah.
So x1 and x2 are two different points, right? And you write P.
No. There's only one point P. So this is the area where, so this is the intersection of the two open sets U1 and U2. P is any point which lies within that intersection. P has coordinates x1, that is mapped by phi1 into x1, and P is mapped by phi2 into x2. So these are two different coordinates, this and this, but they represent the same point.
Yes. So when you write P equals to phi1 inverse, there would be x1 in it, right? So how can you write phi2 P?
Oh, because P is equal to phi2 inverse from here.
Yeah, but it would be phi1 inverse of x1, right?
Of x1. So, yeah, but it's also phi. Sorry, what did I write down over here? Oh, yeah. So, we can do it. Okay, look at this equation. P is equal to phi2 inverse of x2. So, mm, wait. Wait, what did I do wrong over here? So this is correct and this is correct, right? So let's wait. Let me do this again. So x1 is equal to phi 1 of p, which is phi 2 inverse of x2. So this is very good. Thank you for pointing this out. So this, think of it this way. This is some function of x2. So knowing x2, I can get to x1. And you can invert this and you can write this as x2 is equal to f of Should we work out an example so as to make this more solid? I think I should. No, it's important. It's important, you know, how to do this. Thank you for, I should have. So the point is that if I know the coordinates x2, I know the coordinates x1. Correspondingly, if I know the coordinates x1, I can get to x2. Let's work out an example. What's a nice example to work out? Let's work out the case of a circle. X squared plus y squared equals 1. Okay, now let me define the coordinate t as y over 1 minus x squared, 1 minus x. In the open set, so x is less than 1 and greater than minus 1. So this is an open set, right? It's open at both ends. And S I define as x. No, I define it as y over 1 plus x. 1 plus x. Is that okay? Okay, that means from these two, s into t, I multiply this with this, I get y squared over 1 minus x into 1 plus x, which is 1 minus x squared. But 1 minus x squared is equal to y squared. So this is y squared over y squared, which is equal to 1. And so therefore, st is equal to 1, which means s is equal to 1 over t, or t is equal to 1 over s. Okay. But why did I restrict myself to open sets over here? Yes, very good, very good. You see, if x was equal to 1, then t would be infinite. If x was equal to -1, this would be infinity. So keep them, make them open, but do they overlap? Do the sets overlap? Oh, yeah, of course they do. They have lots of points in common. Yeah, so actually I could restrict it this way. I could say, okay, maybe U1, let me be more specific. U1, I take x to be less than 1, greater than -half. And U2, I take x to be greater than -1 and less than 3/4, let's say. So x is less than 1, which means this will never be 0, never be infinite. X is greater than -1, so this is fine. And now what is the intersection of U1 with U2? So there are, you can see that there's an overlap between them. So that illustrates what I was trying to do in a very general n-dimensional space. I defined what is called a coordinate chart, but now I will define what is called an atlas. So this is a collection of coordinate charts that completely cover the manifold M. What does it mean to say cover the manifold? That means every point of the manifold is included in the atlas. So if you have your manifold, and every single point has to belong to at least one open set over there. That's pretty obvious. And how many coordinate charts would you need to cover a circle? Is what is called S1. So how many coordinate charts do you need to cover this? 2. Yeah, because there's we just saw that over here. With 2 you can cover it.
You can also cover it with 4 also.
You can cover it with 4, with 3. There's no limit on that. At the minimum, you need 2. Yeah. And for a sphere also, you will need at least 2, because there's
Talking about the stereographic projection.
stereographic projection. So the atlas is just as you need to just cover the whole space. One final point before we go. By the way, all this is contained in the written lectures, and you can get to those written lectures by clicking on each lecturer here at the school. So I think all of us will in time put up our notes over there. And those notes may have much more than is covered in the lecture, because in the lecture we can only spend a little time talking about the details. The one last point that I want to cover before we go is that, okay, let's take this S1. If I take a point over here, let's say here, then a tangent vector, so I'm looking at it from outside. A vector will be pointing like this from this. But this vector, we can see that this is a curved space because the vector has left the space. Let me draw it longer. I draw a vector and it has left the space. This is curved, but there's a name associated with that. It's called extrinsic curvature. So you and I are living in 3 dimensions, and this over here is in 2 dimensions, and we see that a vector cannot remain on S1, and so this is curvature from outside, extrinsic. But there's another kind of curvature which is called intrinsic curvature. Same point P over here, but now think of the ant. We've been talking about manifolds and ants on the manifold. Well, think of a sphere actually, that's even better. Can the ant ever know that it is living on a sphere? So you mean that we humans can never discover that we are living on an earth which is round?
We can go in the Z direction.
So look, the difference is this. In this case, we are looking at the ant. The ant can maybe also tell what is up and down. So here, in this case, the ant can look up and it can't look down because, okay, it can look up. In this case, the ant cannot look up, it can only look ahead. So it can look this way. So just like, imagine we can't see the sky. Okay, if you can see the sky, maybe you can make out that we live on a curved sphere. But what if you could not look above, you could only look straight? Then would you ever be able to tell that you are living on a curved surface? Yeah. So can you use the microphone? See, otherwise your voice will be lost to posterity.
I was saying that you can start off and mark that point, and then you keep walking until eventually you will reach that same point again. Then you know that you're on a curved surface.
Okay, so if you come back to the same place after walking a very long time, you will certainly know that you are on a sphere. Yeah.
On a curved surface, at least, not necessarily a sphere, but a curved surface.
I think it has to be a sphere. If you keep walking like this, and you have marked your initial point, then you will come back to the initial point only on a sphere.
But on a circle as well, you can go around.
On a circle as well. Yes. S1 or S2 or S3 or Sn. Okay, all that. But okay, the things that we will discover is that you don't have to take a walk all around the world, all around the earth. Even living in a small patch, we will be able to discover. But how to discover that, that will be the topic of many lectures to come. So, एक मिनट. इधर यहाँ इनको. Okay.
Sir, I'm saying that if you have two ants that are on the equator.
Two ants?
Yes, sir. And they start moving from the equator upwards.
Don't talk about two ants, because then there'll be communication between them. No?
No, sir. It's just that they'll eventually arrive at the same point going parallel. And that would give them reason to believe that parallel lines are moving closer together and meeting. If you move from the equator upwards towards the North Pole.
Yeah, but they may arrive at different times. They'll need coordination between them. So let's stick to one ant. Okay. Then you have any further comment on that? Okay. Any other comment? No?
Sir, what if we draw a triangle and see the sum of the angle is 180 degree or not? Even in the small patch.
You are stealing my thunder. वो बाद में पता चलेगा यार.
Right.
Yeah.
Sir, following up on his point about the triangle, is there a minimum amount of area that you need to be able to show that the triangle's area is not like sum of the angles is not 180? Because like I can make a small triangle on the ground and it would still be 180. Is there a minimum area that you need to cover?
No, actually, you would not find 180. Not in this room. It depends on how accurately you can measure your angles. Okay. What if I find it to be 180.00009? So then the accuracy with which you can measure angles will be critical. With a protractor, of course, and in school it doesn't matter, but we're talking of something theoretical. Wait.
No, but sir, when you said that we are in a manifold, there is local flatness, right? Mm-hmm. So Euclid's laws work at some point if we zoom in close enough. Mm-hmm. So there's a point if you make a triangle there, then its angles would add up to 180.
Never.
No, you are talking about the sphere or just a plane?
Sphere. Local flatness.
They will always be bigger than when you take geodesics.
Okay.
No, we don't even know what geodesics are right now. He just says you draw a straight line, triangle. Okay, geodesic. Okay, now.
I'm saying then it will not add up.
Okay. But you said that we will have local flatness. And now you're saying that we can't have that. We can't have Euclid's
We will
laws.
approach local flatness.
Okay, okay.
Okay, we will never have complete. We will never have exactly 180 degrees. The sum of angles adding up to 180. Never have that, except for a triangle of zero size.
Okay.
But we will get closer and closer to 180 degrees, depending on on how small a triangle we choose.
Okay.
That's the beauty of limits. एक मिनट.
Sir, what if we take derivative with respect to space and then find out if it's zero or not? Then we can get to know that if it's a curvature or a flat space.
So how do you take derivatives? You take a point which is close by, and then whatever function there is, you take the function here, function there, divided by the distance between the points, right? And yeah, if you can calculate the derivative, if you can measure the derivative, then yeah, you will know everything. And maybe you will need to calculate the second derivatives. So in fact, for calculating curvature, it turns out we need second derivatives.
Right.
The first derivative is not enough.
Right. And sir, when we talk about intrinsic curvature and extrinsic curvature, can we take these two for one specific shape? Like, can we, for a single shape, can we talk about these two concepts simultaneously?
Okay, so suppose you have this sphere in what we would describe as a sphere, and this is embedded in a four-dimensional space.
Right.
That will be one situation, and R being confined to 3 dimensions will make that same object have a different, it will be a different manifold there. So you have to say in what dimension space a particular manifold exists.
Right. So like we need to consider a reference point. We need to fix our reference point before saying that if it's a intrinsic curvature or extrinsic curvature.
No. That is set from outside. First of all, you will have to say in how many dimensions do you live?
Right.
Okay. And then is that surface in the same number of dimensions? Has to be.
Right.
He's referring to Gauss's theorem, I think that's the average value of the curvatures.
Oh, okay.
No, you multiply it, yeah.
Kappa 1 into kappa 2, yeah. Yeah.
So would you say that
Yeah, go ahead.
Would you say that you need to go always one dimension higher to tell if it's intrinsic or intrinsic?
1, maybe 2. Look, if I'm in 3-dimensional space, I can always draw a 1-dimensional manifold, can't I? Which is a line. I can draw a 2-dimensional manifold, which is a circle. But I'm living in 3 dimensions.
I think the whole point is if you can define what a curvature is, then you'll start seeing things. So first of all, what's the curvature of a curve?
Yeah, so we will come to definitions, mathematical definitions of curvature very soon. But before that, we've got to get a lot of other work done. The next thing that we have to talk about is tangent spaces.
I think this question is about that diagram that, to define extrinsic curvature, there has to be a dimension outside.
Yeah, okay. So with reference to this diagram over here, I am living in three-dimensional space, and I can see this vector as going straight and not being on S1. So because I'm living in a higher dimension, therefore, I will call this thing extrinsic curvature. I will say that this line is zero curvature. It's not curved, it's straight. So I'm at this point over here, just like I'm at this point over here. You can see visibly that this vector is no longer on the manifold itself, whereas this vector is on the manifold. So no curvature and plenty of curvature here. This is different, very different, because it's now an ant which cannot look up, cannot look down, can only look forward. How will this ant get to know that it is living in a curved space? And you know, all of this becomes very important because what Einstein discovered was that we live in a four-dimensional space, so three coordinates x, y, z, and there's time. And that space is curved. That space becomes curved because of the presence of matter. General relativity is all about that. More matter there is, the more curvature there is. But Einstein didn't go to 5 dimensions. He said, we live in 4 dimensions. We cannot go to 5 dimensions. And the space in which we live in is curved. And so you can ask, how do you know? And he showed how you can know that. Now you can go to 5 dimensions, and Kaluza and Klein did that. They found interesting things which relate to quantum mechanics, but we won't get around to talking about that, unfortunately. Okay, so we are done for today.